Okay, so unit 4 is on stoichiometry. I mentioned this on Monday, but let's talk about this now. So stoichiometry is basically it's a mathematical relationship between the products and reactants. Mathematical, meaning we're going to do conversions, just like we've been doing all semester. And I want to remind you, these 4 steps are particularly important for units 4 and 5. Now, unit 5, we're going to be getting into solutions, things like concentrations. And again, it's going to be a molar relationship. Things like if you put 5 grams of sodium chloride in 2 liters of water, what's the concentration? That stuff. Bless you. All right, so stoichiometry again is the mathematical relationship. Now, as I stressed on Monday, you're going to see a pattern developing today. I want you to key in on that pattern because the pattern is going to be replicated every single time, which is basically 3 steps, 3 conversions at a minimum. Sometimes there's a more, depending on if you have to do an additional conversion or not, but usually it's 3 steps. Okay, so let's take our good old methane, CH4, and burning it in atmosphere, and we produce carbon dioxide and water. Step number 1 is always check the equation, chemical reaction for balance. Is it balanced? No. It's balanced now. Okay, what's the given? Okay, let's look at this one here. 34.5 grams of water is formed. How much oxygen is used? Okay, so we're looking at water and oxygen. Okay, so what's given again? 34.5 grams of water. And we're trying to calculate oxygen gas. Now, in this class, I'll always say oxygen gas. I've been saying this throughout the semester, but if you just see how much oxygen is used, it's oxygen gas. It's never just plain old oxygen. There are 7 gases that are like that. Oxygen is one of them. Hydrogen, nitrogen, and all the halogens, chlorine, bromine, iodine, etc. Those are all diatomic gases. Okay, so what's given? 34.5 grams of water. What are we trying to calculate? Oxygen, grams of oxygen. Okay, so the problem up to now has been we've never had a chemical reaction when we've been doing conversions. Well, now we are going to have a chemical reaction doing conversions. So there's a middle step there. Remember I said there were 3 steps? Okay, the middle step, the second step is where the balanced equation comes into play. Okay, so we have always convert to moles. Okay. Now 18.02 is only for water. On the test, question number 1 said NH3, and a lot of you have been on 1802. So it only applies, that's the molar mass from the periodic table. 1 carbon, excuse me, 1 oxygen, 2 hydrogens. Okay, so now we have moles of water. Now we need to go from moles of water to moles of oxygen, and that's where the balanced equation comes in. Okay, so we have calculated over given ratio of the coefficients from the balanced equation. So we've got calculated is O2 on the top, water on the bottom. So the waters cancel. And we're going to looking at the coefficients from the balanced equation. These two guys. And it's 2 to 2 or 1 to 1. Now we've got moles of oxygen gas. We want grams of oxygen gas. So we're going from moles to grams now. Oxygen is 16.00 each one, and there are two of them, so that's 32. So now we're at grams of oxygen. So we multiply everything on the top, divide by everything on the bottom. We're looking at 34 I. Oh, yeah. Now, do I have to multiply by 2? 2 over 2 cancels. So basically, if you want to multiply by 2, make sure you divide by 2. But 2 over 2 is 1, so we don't have to worry about that. Okay, times 32 divided by 1802 on the bottom. Enter. Now, those are the 3 steps. Whatever's given, convert to moles. Boom. Coefficient ratio from the balanced equation. That's in the middle. And then convert to, using conversion factors, convert to whatever you're trying to calculate. So you're going to go from moles So given to moles, coefficient ratio, moles to calculated. All right, are there any questions about what I just did? Now, we haven't really done a whole lot different other than the middle step. Yeah. Determined what? Okay, how many sig figs is that? 3. What about that? 4, 1802, 1802. What about this? The middle one. What's the sig figs in the middle one? Infinite, because there's exactly 2. Not 2.1, it's exactly 2. Okay, so that's infinite. And then over here, it's 4 sig figs. So we have 3, 4, infinite 4, so it's 3. Okay. All right, any other questions about this? Oh, I got the numbers. Now, I've been really pushing this conversion throughout the whole semester. So this is not, shouldn't be a giant leap. Now, test 4 is going to be very focused. It's going to be stoichiometry, nothing else. So the alternate lab I gave you, alternate dry lab, this one here, make sure you do that for Monday's tests. I'll do it because it's for 15 points lab, but it'll really help you on your test. There's a lot of practice there. Okay, so let's do a lot of these now. Okay, we have 45.6 liters of water vapor formed. How many liters of oxygen gas was used? This is all at STP, of course. You know, we're using the same balanced equation. So let's write this right here. Okay, so step number one is balance equation. Boom, done it. Okay, what's given? 45.6 liters of water. And we're trying to calculate liters of oxygen gas. Step number one, liters to moles. How many liters are in 1 mole of any gas? Yeah. No, that's how many liters of gas? Yeah. 22.4. At STP only. If it's not at STP, then we have to use the ideal gas law in there. So that makes it much more complicated if it's not at STP. Okay, now we're in moles. Now we need to go from water on the bottom, oxygen on top. So now we're going to go from moles of oxygen gas to liters of oxygen gas, also at STP. Yeah. If it involves burning methane, yes. Yes. Methane CH4, burning it in will be in an oxygen environment. That'll be the same equation. I could have said how many liters of oxygen, well, how many liters of methane was used. In fact, let's do that. Let's change it. So what's going to be different? We still have the same given. What we don't have is the, this is going to be now and this is going to be 1. Oops. But we're using the same chemical reaction though. But there's millions of chemical reactions. So you have to know, I have to give you the chemical reaction. You're not going to just always use the same one. No, it's still the same because the reaction hasn't changed. Same reaction. So if it's 2, and one problem with water, it's going to remain 2 until you reword the question. Okay, so what is this going to be? 36 figs again. Notice the 22.4 canceled out, so you didn't have to put that in your calculation. I'm sorry, what? 36 figs, yeah. Okay. Notice again the same pattern. What's given, convert to moles. Mole ratio with the coefficients from the balanced equation, and then you convert to what you're trying to calculate. 3 steps. Okay, same reaction again. And we have methane and oxygen gas equals carbon dioxide and water. And how many molecules of carbon dioxide is created? We start with 34.5 liters of water. And we want to know how many molecules. What conversion factor are we going to be using for that? Whenever we want to know how many, think Avogadro's number. Okay, so first step is convert to moles. Since we're using a gas at STP, we can use 22.4. All right, next we need to look at the coefficients for water on the bottom, carbon dioxide on the top. And now we have moles of carbon dioxide. We want to go to how many molecules of carbon dioxide, Avogadro's number. Okay, first step, convert to moles. Second step, coefficient ratio from the balanced equation. Last step is convert to calculated from moles. So okay, these are the conversion factors you're going to be using. Molar mass from the periodic table. Gases at STP, that's 22.4 liters per mole. And then Avogadro, no, this is for all gases. And Avogadro's number, And of course, we have the inversions. This is a list of the diatomic gases. There are 7 of them. So again, in my class, I always say oxygen gas, but in other classes, they may just say oxygen. And you need to know, oh, that's one of those diatomics. Di meaning 2 atomics. Okay, so there's hydrogen, nitrogen, oxygen, and all the halogens. So that's fluorine, chlorine, bromine, iodine. These guys, all right, now this problem, how many kilograms of carbon dioxide is produced from 23.4 liters of oxygen gas? This is a 4-step problem because of the kilograms. And then we want kilograms of CO2. Okay, convert to moles, step number 1. And whenever we have gases in this class, unless we talk about specific ideal gas law stuff, it's going to be, when we convert to moles, it's going to be 22.4 liters. When you get to 1A, 2A, or 3A, you're rarely going to have STP gases. You'll start off with that and then quickly move on to non-STP gases. Okay, so again, that's the equation. Okay, so the oxygen needs to be in the bottom. And we need to have carbon dioxide on the top. Okay, so that's 1 to 2. Now we want to go to grams first because the periodic table is calibrated in grams per mole for carbon dioxide. Carbon dioxide is going to be okay, so that'll give us grams of carbon dioxide, but not kilograms. How many grams are in a kilogram? Right, 1,000. Okay, does everyone see why this is a 4-stepper, not a 3-stepper? Because of that last conversion. But the meat of the thing is an original 3-step pattern. Convert given to moles, coefficient ratio balanced equation, convert to what you're trying to calculate, Again, 3 basic patterns here. And then in this last step, we had to convert to kilograms. Yeah. Mhm. No, it's the coefficient from the balanced equation. So the coefficient for oxygen is 2. Now there's 4 atoms of oxygen, but we're not trying to calculate atoms right now. We can do that as an additional problem, but right now we're just worried about the middle step. Is just strictly from this is the reason why we balance the equation, is for this exact step. You see why it's 2? Okay, now there are 4 steps: stoichiometry, balance equation, what's given, what are you trying to calculate, and then the setup. Sometimes there are 2 givens. So look for that. If there are 2 givens, this is a whole lot different problem. Okay, so why don't you try doing these guys on your own? Change seats. You change seats.
Oh, yeah.
Yeah, Closer the better. So what about it? It's not balanced though. You have a 2 there and a 2 there. Yeah, that's the first step, right? You're working on the pre-lab. Yeah, I know. You can. She's not here today. Hmm? Yeah. I'll be giving your test back in lab like last time. Okay, is everyone, you need more time? All right, see what these look like. All right, how many grams of water produced of 5.67 liters at STP, of course, of carbon dioxide produced? So we want water, and we're starting with carbon dioxide. Now we have moles of given and want to calculate water and we're coming from CO2. Okay, now we have moles of water. Okay, and water is 18.02 from the periodic table. Only water is 1802, nothing else. Okay, so everything cancels except for grams of water. Okay, this guy, what's different about this one? Two givens. Two givens. All right, so I'm going to stop for a second, ask you this. If I have, let's go back to our bicycles now. We're going to build bicycles. I've got 10 frames and 10 wheels. How many bicycles can I make? 5 bicycles. 10 frames, 10 wheels. Why not 10 bicycles? Don't have enough wheels, right? So what's limiting the amount of bicycles I'm making? Wheels or frames? Wheels. So that's the limiting reactant, are the wheels, because it produces the least amount of product. In this case, a complete bicycle. So in your mind, you're going, how many frames are on one bicycle? One, right? So 1 to 1. So excluding the number of wheels, I could make 10 bicycles. Excluding frames, now let's look at wheels. In your mind, you're going, well, it takes 2 wheels for 1 bicycle. I have 10 wheels. That means I make 5 bicycles. So you did that calculation in your head. It was really tough, I know. Did it in your head. Now we're going to do the same thing chemically. Well, you're not going to do it in your head. Okay, so let's look at this reaction. Now, it's important to understand how to do it with one given before we go to 2 givens. So what I want to do is I'm going to go through this very slowly, make sure you understand. Now, let's continue on with the bicycle example. Okay, so we know we're only going to make 5 bicycles. Do we have anything left over after we make the 5 bicycles? What do we have left over? 5 frames. So we have excess reactants, excess frames. So there are 3 calculations you need to do, not 1, 3. And each one has 3 parts. Okay, so let's take the reactants individually. Okay, let's start with the methane. And let's see how much oxygen gas is consumed. Okay, first thing is we need to figure out the mass of methane. Who remembers the molar mass for methane? Well, it's 1201 and then 404. So what is that? 1605. Okay, now we have moles of methane. Methane's 1, oxygen's 2 from the balanced equation coefficients. Okay, and we're going to convert to grams of oxygen, and there are 2 of them, so that's 16 times 2 is 32. So if we had only methane present, this would be how many grams of oxygen would be consumed. Okay, 22.6 grams of oxygen. Oh, we're actually trying to calculate water, not oxygen. Ah, sorry about that. Okay, 12.7. Now we're going to go and take the oxygen, excluding the methane. Now this is assuming there's nothing else going on, and we just had one given. That's 5.67 grams of methane. Now we're looking at oxygen, same way, same kind of calculation. Starting with oxygen, okay, the front end is going to be different. The back end of that can be the same. Okay, so we're ignoring now, when we do these two calculations, we're ignoring the other given. Okay, so clearly there's a difference there. Which one produces the least amount of product, the least amount of water? Oxygen or methane? Oxygen, it's 295 versus 12. So it's clearly different. So which is going to be in excess, methane or oxygen? Methane is going to be in excess. So the oxygen is going to be totally used up. And we have leftover methane. So the next calculation is how much is left over. How much of the methane did we use if we use 5.23 grams of oxygen? Okay, so we're starting with oxygen, and then we're going to calculate how much methane is used. So we've used 1.31 grams of the methane. The next calculation. So we started with 567. We have 4.36 grams of excess methane. So you have four calculations. One super simple, but you have four calculations. And typically you use a page of notebook paper per limiting. This is called a limiting reactant problem. When you have two given, limiting reactant. One of them limits the amount of product you're producing. The other one is in excess. Rarely do you have exact amounts. Now, this is what car manufacturers do, is they want to produce the least amount of pollutants and get the most power out of their engines. So what they have to do then is to figure out the ratio of oxygen to gasoline under differing temperature, atmospheric pressures, etc. That's what the computer in your car does. But it does not want to have any excess stuff around, because the excess stuff is called pollutants. So chemical engineers work with engineers, mechanical engineers, to produce these engines that produce very little pollutants. They produce just plain old water, plain old carbon dioxide, not some of the other stuff, not carbon monoxide or plain old carbon. Now, as an exercise, next time you start up your car when it's cold, you start it up and run around to the back and look at the tailpipe. You'll see water dripping out. And after it heats up, the water doesn't drip anymore because it turns to steam, but you have water produced in your car all the time when it's running, of course. Okay, so that's what I wanted to cover today. I'm going to go into this in more detail tomorrow. One thing I'm going to show you is extra practice. So if we go to Unit 4, stoichiometry, these are extra worksheets. Some are on equation balancing, gasoline combustion, gram to gram stoichiometry. What I mean by that is you start with grams, end with grams. Gram molecular stoichiometry. These are all worksheets. And I've got a bunch of limiting reagent or limiting reactant worksheets also. Limiting reagent beginning would be a good one to start on if you want more practice. But tomorrow we're going to go into this again. Now, tonight, it would be really helpful if you did the dry lab. Does it really help for tomorrow? Because we're going to get into this again and again. This is crucial you understand this. If you don't understand this going into 1A, 2A, or 3A, you're not going to do well at all, because they're going to assume you're very familiar with this. And they're going to move along very fast. That's one of the problems with 1A, 2A, and 3A if you haven't had a prep class. And the problem with the number of prep classes we offer in this school is I'm it. I'm the only one that teaches this class. Now in the fall, there's going to be another person doing it. So there'll be 3 sections. We used to have 7 sections when I first started here. And then we didn't have enough professors to go around. So they kept eliminating this class. And I kept telling them, I want to teach Chem A. I like Chem A because I know what is needed for students going into those more advanced classes. Okay. All right, so I'm going to end here. And again, we're going to hit this hard tomorrow.